Welcome student to fourth lecture in this series. So today we are going to discuss conservation laws. Okay, conservation laws. In this conservation laws, there are two types. One is called as exact conservation law, and another one is called as approximate conservation law. Now, what is the difference between exact conservation law and approximate conservation law? This exact conservation law means this has to be conserved in all the reaction. It is necessarily conserved. It is necessarily conserved in all reaction. In all possible reaction. That means if exact conservation law is not conserved, then the reaction will not take place. It will never take place. So this exact conservation laws has to be conserved. Now the approximate conservation law are the conservations which may or may not be conserved, which may or may not conserve. That means if any of these approximate conservations are not conserved, then also reaction is possible. Okay, so now let us see the exact laws. Okay, conservations of physical quantities. So as far now we know some physical quantities such as charge, then we have mass, then we have momentum. Mass is nothing but energy. I am talking about energy. We have momentum, we have baryon number, lepton number, and then we also have something called as CPT. Okay, this is charge conjugation, parity, and time reversible multiplication. These three are the operators. This is a charge conjugation operator, P is a parity operator, and T is a time reversible operator. We will discuss in detail about this CPT. And then we have isospin, we have third component of isospin, and we have strangeness. Now these are all exact. These all physical quantities are exact conservation, so it has to be conserved in all possible interaction. So we are going to talk about three interactions. First is strong interaction, EM interaction, that is electromagnetic interaction, and weak interaction. We know there are four types of interaction: strong, EM, weak, and gravitational. So gravitational is neglected here. So strong, electromagnetic, and weak interaction, this all has to be conserved. This all are exact. So this all are conserved in strong as well as in weak and as well as in electromagnetic interaction. But this isospin, these are these three are approximate conservation, so it may or may not be conserved in the reaction. Okay, but in strong, all these three are conserved. This all three are conserved. This isospin is a vector addition. Okay, whenever we find an isospin, we need to do a vector addition. So you must be knowing we used to do 1 bar plus 2 bar is from 1 minus 2 to 1 plus 2. So this was a vector addition. Okay, so in the similar fashion we have to do for the isospin. So these are the vector additions. Okay, and this isospin is algebraic. You can directly sum this up, isospin, and strangeness is also an algebraic property, so you can always sum these two up. But isospin you need to have a vector addition, and for CPT you need to have multiplication. For CPT this needs multiplication. When we solve some questions on this, based on this, you will get to know what I am talking about here, that is why this property are multiplicative and why this is vector addition. So in strong interaction, isospin, then third component of isospin and strangeness, all three are conserved. But in EM, this isospin, the vector isospin, is not conserved, vector addition wala, and this third component of isospin is conserved, and the strangeness is also conserved. Strangeness is conserved means delta S is 0. Delta S is 0. But in weak interaction, nothing is conserved. Isospin is not conserved, third component of isospin is also not conserved, and even strangeness is not conserved. Strangeness may or may not be conserved. Okay, in weak interaction, strangeness may or may not be conserved, but the condition is delta S must be 0 or plus minus 1. That's it. It cannot be greater than plus minus 1. Okay, the strangeness must be in the range of 0 or plus minus 1 in the weak interaction. So these are some conservation laws. There is one more conservation, approximate conservation, which is called as CP, charge conjugation and parity multiplication. So this charge conjugation and parity multiplication is conserved in strong interaction as well as in electromagnetic interaction, but is not conserved in weak interaction. It is not conserved in weak interaction, but for strong and electromagnetic this CP is conserved. So with CP, strangeness, isospin, and third component of isospin, you can easily find out which type of interaction it is. And with the above this four exact physical quantities that has to be conserved, you can easily find out is it a reaction possible or not. Okay, so this is it. If any doubt is there, you can always ask in a comment section. Then moving further on, let us understand what is parity. Okay, parity, charge conjugation and time reversible we will understand, and their multiplication and individual conservation. Okay, always here also there will be a charge conjugation, parity and time reversible separate. That also is conserved in strong interaction. Okay, but in weak interaction and electromagnetic interaction there is a variation. So we will consider only this four approximate conservation. Parity operator, whenever it operates on psi RT, it is converted into this this psi RT is converts into minus RT. Okay, minus RT, and this eigen value of this parity operator may be plus 1 or minus 1, because when you see psi minus RT, this psi minus RT may be plus or minus psi RT. Okay, plus or minus psi RT. Okay, so the eigenvalue for this parity operator, is plus or minus 1. Eigenvalue for the parity operator is plus or minus 1. what is the significance of this parity operator? It shows the mirror refraction. It shows the mirror reflection. That means, is this wave function is having a mirror symmetry or not? If it is having a mirror symmetry, then the eigenvalues, if there is a mirror symmetry, if there is a mirror symmetry, then the eigenvalue will be +1. If it is there is no mirror symmetry, then the eigenvalue will be -1. So this is about parity operator, and this is how it is operated. And if you want to discuss parities of the elementary particles, so mesons have negative parity, because pseudo scalar and vectors are always in negative parity in nature. If there is a pseudo vector and scalar, then it might have been +1, but for mesons there is pseudo scalar and vectors. Pseudo scalar and vectors are there. Pseudo scalars and vectors, right? We have seen that the pseudo scalar has angular momentum 0, total angular momentum 0 and parity -1. Vector had total angular momentum 1 and parity -1. And for baryons, this parity is positive. That means we have already seen this, that is half positive, that was baryon octade, okay. And then we have also seen 3/2 positive, which was baryon decouplate. So this way we have seen the total angular momentum and the parity as well, so it is easy to remember. Then leptons are again positive parity. Leptons are having positive parity, then baryons are having positive parity, but this mesons are having a negative parity. Furthermore, if you take the antiparticles, that is anti-meson, the anti-mesons and meson both will have same parity. That means that is you need to note this very important point. Note it, that anti-boson and boson will have same parity, and see, this is bosons, integral spins are there, so it will have a same parity, that is -1. Anti-meson will also have -1, and meson will also have a -1 as a parity. But anti-fermions have different parities. That means, if we talk about anti-baryon now, so anti-baryon will have a additive inverse for this, so that is anti-baryon will have negative parity and anti-lepton will have negative parity. Okay, so this is baryons, anti-baryons, leptons, anti-leptons, mesons, anti-mesons. One thing to note, that bosons will have same parities. If it is +1, then anti-boson and boson will have +1. If it is -1, then anti-boson and boson will have -1. So meson, since it is having -1, so anti-meson will also have a -1 as a parity. But fermions like baryons and leptons will have a different parities for antiparticle and particles. Now moving on to charge conjugation, that is C operator. Okay, this C operator, whenever it is acted on particle, whenever it is acted on a particle, it changes its charge. Charge is changed. Okay, so q becomes minus q. Q becomes minus q. Okay, and with this change in charge, it becomes, its baryon number is changed, then its lepton number is changed. If it is a baryon or a lepton, then it becomes a antiparticle. Then it becomes an antiparticle. Okay, see here, whenever there is a charge conjugation operator, whenever it operates on a particle, it changes its charge. Okay, if it is a if it is a baryon or a lepton, it will change its baryon number as well as lepton number. Okay, and it will become an antiparticle. So it is an antiparticle now. So basically what C operator does is, this charge conjugation operator does is convert this particle into antiparticle. Now you can easily see this state is not same as this state. So this is not that means it is not an eigen state. It is not an eigen state. It is not an eigen state. Okay, if it is not an eigen state, there is no question of eigen values and all. So this is not an eigen state. The C, when operates on a particle, it does not get into an eigen state when if it is baryons or leptons. Okay, but if it is mesons, then this charge conjugation operator acts in a different way. That means charge conjugation when acted on a meson, let us take any meson, let us take pi 0, let's say. So when it is acting on a pi 0, it will give you pi 0. Okay, since the charge is 0, so charge is not changed. So charge is not changed, and the eigenvalue for this will be plus 1. Eigenvalue for this will be plus 1. Okay, now only for the mesons, only for the mesons there will be an eigen function, eigen state. For baryons and leptons there won't be an eigen state for this. So whenever there is an baryon and a lepton involved in the reaction, we don't usually check for C. But if there is no baryons and leptons involved, there is only mesons, so we can always check for C. So there is one rule for a eigenvalue of C, that is eigenvalue of C is minus of this C plus S minus 1 to the power S. So the that S is different for pseudo scalar mesons and vectors. So for pseudo scalar mesons this is 0. So for all pseudo scalar, the eigenvalue for C plus is plus 1 for all pseudo scalars. But for vectors, this charge conjugation will be minus 1, because S is 1, so it will be minus 1 for all vectors. Now as we have already talked about, if there is no baryons and leptons involved, then there will be an eigen state for C that we have seen for the mesons, as well as it will be for the gamma particle as well. So in a gamma, so this, if it is operating on a gamma, then the charge conjugation for this gamma will be negative 1. Okay, the eigen state for the gamma is negative 1. And one more thing, the charge conjugation of n gamma particles released will be minus 1 to the power n gamma. Okay, so these 3 points you need to remember, that charge conjugation of gamma is negative, charge conjugation of n gamma is minus 1 raised to n, Then for the mesons, you need to remember -1 to the power s, that is for the pseudoscalar. Charge conjugation will be positive and charge conjugation will be negative for the vectors. Parity is negative for both pseudoscalar and vector, but charge conjugation is different. Charge conjugation is 1 for pseudoscalar, and vectors it is having charge conjugation -1. Okay, if we see here Cp for pseudoscalar, if we see Cp for pseudoscalar now, for pseudoscalar if you see Cp will be nothing but +1 into -1, that will be -1. And if you see Cp for vectors, if you see Cp for vectors, then for vectors it will be -1 into -1, that will be +1. Okay. So this Cp, what I was talking about in a conservation law, approximate conservation, that if you are having some reaction given, let us suppose we have a reaction that is W naught meson is getting converted into pi meson plus gamma, and one more reaction you have, that is W meson is getting converted into pi naught plus gamma plus one more gamma. Okay, so in these two, which reaction is possible and which reaction is not possible? So if you see the charge conjugation here, so the charge conjugation for this W meson, W naught meson, since it is a pseudo vector, it is a vector, this is a vector, so the charge conjugation will be -1. Okay, this pi naught is a scalar, pseudoscalar, then the charge conjugation for this is +1, and this gamma is having -1, so if you multiply this both, so it will be nothing but -1. So charge conjugation is conserved here. And here it is of course not conserved, because it is 1 -1 -1. So if you multiply this all three, you will get +1. So it is not conserved here. Okay, so it is this reaction is in a high potential that it can be a strong interaction. Okay, so this is a one example to understand what is charge conjugation.